Hello everybody, welcome to the next video on the series of Physics at Home. Today's lab is about friction. As this block is sliding on the surface of this table here offers some friction that resists the motion of this block. Now there are two kinds of frictions, there is a static friction and kinetic friction. The difference can be seen here again with this block. I'm trying to push this block. Not a whole lot of push, but trying to push it, but it's not moving. But until I apply a minimum amount of force where it breaks free, until that point of time, the contact surface, between the block and the table here, they were not sliding past each other. But once they slide past each other, it was a different story. So before sliding past, there was static friction in play. After they started sliding past each other, there was kinetic friction. Now, static friction we could see on this block, on this track here. Okay. So right now, let's say, put it like this. If I do this, okay. Right now the block stays at rest there. Even though we know there is gravity pulling it down, the block stays at that point. So unless we lift it at a certain, some distance or some tilt, you can see now the block is moving, but it stops again and again, so on and so forth. So at a certain angle, we can see that, this can move or slide down. Now, this is where the pull by the gravity is nearly equal to the friction. But as you can see now, it kind of is varying, and also the track is bending and things like that. So it is going to be, if we had known, calculate the angle here, that angle would have been related to the what we call as the coefficient of the static friction, which is nothing but a measure or a characteristic of the block and this plastic track, that how rough it is. Okay. Now, because the block could start moving at different angles, so you can see now it stop here, but again we tilt, again it moves. So quantifying static friction could be a bit tricky. Okay. So in this lab we're going to concentrate only on kinetic friction. Okay. Now kinetic friction is when we know that the block is already sliding, but there is some resistance. And to quantify it, I'm going to tilt this track much more. Let's put it like this. Use my support in the middle. So this stays here, over here. That should be plenty. And then if I put the block, I want to make sure I'm using the same surface always, which was this one. If I put it here, we can see it can start from rest and speed up. Right? It's going to be similar to the gravitational acceleration lab, but we're going to go into a little bit more details. The car we had used previously had almost no friction, so we could get away with thinking that, oh, there is a zero friction situation. In this case, we want to intentionally make it rough so that we can quantify how much is the coefficient of kinetic friction. And to do so, we're going to follow the same procedure, that I'm going to get my stopwatch and then measure 3 times how long it takes to go from the start to the bottom. Okay. Now in this case, I have put a block here in the end so that this one does not fall off and I don't have to pick it up. So when I put it here, then I want to know the distance from this edge to here, correct? And earlier I know that the track is about 52 centimeter, so I want to measure up to this edge how much it is from this end. So it's about 5 centimeters. It's about 5 centimeters from here. So 52 minus 5 makes it 47. So 47 is the distance that this block is going to cover. Alright, so let's measure 3 times. Okay, let me go back to the same surface. So start here. Alright, so 1.05. One, two, three, go. 1.08. Let's do one more. 1, 2, 3, go. 1.16. Okay. Alright, so I got 3 times. And in the next section, we're going to see how to calculate the coefficient of kinetic friction. That is the measure of roughness between the wooden block and the plastic track. Okay. In the demonstration, I forgot to mention the height of the ramp. Okay, here. So that was turned out to be about 0.19 meters. Okay. So moving forward, here we see the block on that inclined plane, and W, F, and F subscript N. These are the 3 forces acting on this block. Okay. Now, what we could do to simplify things here is to, this W, we can break it down into 2 components. One which is perpendicular to the ramp, which is this. This is the perpendicular. And then Wx, which is the parallel component to the ramp. Okay. So the parallel component is the one that is pulling it down, and friction would be in the opposite direction of the same. Okay. So as far as perpendicular to the ramp, the normal F subscript N and W subscript Y, these two are cancelling each other out, which in other words would mean that normal force is equals to the Y component of the weight. Okay. Now the angle here is the same angle theta that we see here. Okay. So WY, if we look at this as a right triangle, then WY is the adjacent side in that right triangle, and then WX is the opposite side in that right triangle. Again, this being a theta here, okay, opposite to that theta. So let's write this down. Adjacent side uses cosine, so W times cosine theta. This is from the cosine equals to adjacent over hypotenuse. So if you move the hypotenuse to the other side, then hypotenuse times cosine of the angle gives us the adjacent side. And we know W is mass times gravity, correct? So we can say normal force is equals to mg cosine theta. Now here we're going to introduce the equation for friction. In our case, since the block was sliding, so kinetic friction comes into play, and the friction here, which is in our case is kinetic, is equals to mu subscript k times normal force. So mu k here is the coefficient of kinetic friction, and to calculate this is the goal of this lab. Now we want to know how much is the coefficient. Alright, so friction, if we subscript Fn in here, then we get mu kmg cosine theta. Okay. We're going to leave this here for our reference, and we'll come back to it in a minute or two. So this takes care of forces perpendicular to the ramp. Forces parallel to the ramp, there are two, that is Wx and F. Now Wx is pulling down, friction is pointing up. Okay. So if since Wx is stronger than the friction force, so we could say that the difference between the two, this is nothing but the net force on this block. And from second law, we know net force is mass times acceleration. And since pull down the hill or down the ramp is more, the acceleration is also in the same direction. Okay. So Wx minus friction, which is mg, times mu k times cosine theta equals to mass times acceleration. Now if the y component of the weight used cosine, then x component is going to use the sine. So w times sine theta minus mu k mg cosine theta equals to ma. Again, w is mg sine theta minus mu k mg cosine theta. And since the mass is there in each term, we can cancel it out. So, and we get the equation for the acceleration. So acceleration, which is down the incline, and it turns out to be, it is g times sine theta minus mu k g cosine theta equals to a. And we can get the information for theta. We know g. Okay. Acceleration here we can calculate using the information gathered earlier. We know the 3 times, we know the distance it covers, we can calculate the acceleration, and which was using the x2 equals to x1 v1t half a t square equation. And we know the block starts from rest, so velocity 1 is 0, and we can also say that x1 is 0, and then x2 would be nothing but the length of the ramp. So these items cancel out. Again, we left with x2 equals to half a t squared. So length of the ramp equals to 1/2 times a times t squared. T would be the t average. Again, length we know, and then t we know, so we can calculate acceleration. Once you get the acceleration, you can plug it in here and then reorganize these terms to calculate mu k. So let me just quickly calculate acceleration here. So length of the ramp was 0.47, so 2 multiplied by 0.47. Let me write that equation here. So 2 times L divided by t squared gives us the acceleration. That's about 0.781 is the acceleration. And now I could take this, bring it here, and what I know is, if from these equations, the mu kg cosine theta, that term I'm going to bring to the right and a to the left. So this looks like g sine theta minus a equals to mu k g cosine theta, correct? And then g cosine theta, if I need to move, then this will come here and become g cosine theta. This would be the equation from mu k. Okay. Now looking at the L and the H numbers that we saw, the theta here, I'm going to use this sine equation because I know sine is opposite, which is H divided by L. So then theta would be sine inverse of H over L. So let me write this down again. Use a different color so we can know. And that turns out to be 23.8 degrees. So we have all this information. Now we can just plug it in here and calculate mu k. Alright, so (23.8) minus A is 0.781 divided by 9.8 cosine 23.8, and this would be, oh, there is no bracket here, otherwise it would have cancelled out. So 9.8 is multiplied only with this term. That's a 0.354. 0.354. This is the coefficient of kinetic friction. Now in this lab, I'm not going to look at any percent error or anything, because this is more like a qualitative lab. Although, the mu k is, we can definitely quantify. The static friction could be a bit tricky. So this is it. Okay. Next week, we're going to look at collisions. Have a good one.